Hello and welcome to the Weekly Space Hangout for Wednesday, January 23rd, 2019. I'm Fraser Kane, publisher of Universe Today, and this week we're going to be talking about Planet 9 or not, the lunar eclipse and a meteor, the state of the extremely large telescope, uh, jets from the supermassive black hole at the center of the Milky Way, SpaceX's Starship fell over, and
Boink.
Saturn's rings are surprisingly young, and an artificial meteor shower. Joining me this week, we've got Morgan Renberg,
Hey, Fraser. Hey, everyone.
Kimberly Cartier.
Hey, Fraser. Hey, happy podcast day.
Oh, it only shifted to you at the very last second.
Happy podcast day. I can say it again.
It's the delay.
And Paul Sutter.
I bring peace and joy to everyone.
Worked right at the end. All right, so before we get into this week's episode, I want to give a big shout out and a thank you to all our good friends at the Weekly Space Hangout crew. They are, of course, the producers, the organizers, the people who fill the chat that's below on the show. If you want to join this community, and again, especially now that the Google Plus community that really started the whole thing is going away, go to wshcrew.space. All right, let's get into our special guest. So our special guest is Marco Parigi. Marco, welcome to the Weekly Space
Hello,
Hangout.
everybody.
It takes us a
Hi,
second.
Fraser.
Hey, so where are you, Marco?
I'm in Townsville in Queensland in Australia. So it's in the southern hemisphere, so it's summer here. It's 11 o'clock in the morning and very hot. You probably hear the fan going on. That's probably that whirring noise.
We can
that,
see the
you have
fan
there.
anyway. We can't hear it. So who are you
Yes.
and what do you do?
All right, so my name is Marco Parigi. I'm actually a small business owner here, but I dabble in science and especially in space. And really, the story started in 2012. I saw for the first time the images of Comet Hartley 103P, which is a bilobed comet. And I noticed that it had a smooth part in the middle there. And I figured it had stretched, and but nobody believes me, I guess, in that sense. So I basically was looking forward to the Rosetta mission that was happening in 2014 from that point, because it was visiting a comet, and I had a lot of ideas about what they should find. And lo and behold, also 67P was bilobed and had a neck, and I felt that even being a bigger comet, it was even less likely to have been a collision between two planetesimals, because they tend to squash each other in even very low gravity environments. And again, it wasn't put up as an option from the scientists that were studying the comet. And although I did start to go into the Rosetta blog, which is the very popular outreach that the Rosetta mission was doing, and someone called Andy Cooper also put in some comments regarding the fact that he thought it had stretched, and that's where we sort of started the conversation going. We had a lot of emails toing and froing and seeing the various evidence. And we studied the comet photo after photo. The mission scientists went on to sort of make models, and there's a lot of things that can't be seen on the models, which can be seen if you look at 1,000 photos. And that led me to find some changes on the comet when they released the images from after the perihelion, and so you could compare them with the close images from before perihelion.
I'm just going to bring up the story that you did for the Planetary Society, just so people can see the pictures that you're talking about here.
Yes.
And I'm going to show you the picture here. All right. So
Fantastic.
I'll show you the one you've got, sort of where you're sort of comparing the difference here. So do you want to explain sort of what's going on here?
Yeah. So basically, from the Rosetta blog, they showed a lot of images, and you could also access the images directly. And so you could download an image of a particular area and find one of that same area for after perihelion when the Rosetta got close to the comet again. So and there was this particular part of the it's in the Aniket-Sobek border of 67P where there's a ridge, and I noticed the ridge had certain pattern uh, of ridges on it, and in the after perihelion pictures, there was a straight line along that ridge, and there was rubble underneath the cliff of that ridge, and this was a fairly obvious change to me. And there was a particular blog post by the Rosetta blog which was requesting for user contributions at that time, about 2015, when they were trying to see where the changes were in the comet, and then relating them to the science that they were doing. And now, basically, at that time when this was happening, there was also a paper that came out that was mapping the southern hemisphere of the comet, and I noted that there was a fairly obvious error in the position of the border of the Aniket-Sobek border, because on one image it had it well past that ridge, and on the other image at a different angle, and the image was taken at a different time. I could tell both of them was taken at a different time from the changes, and that it was they put the line in a completely different place. It was about 200 or 300 meters away from where the line was in the other image, and so I myself and Andy Cooper, who also found several more errors on there. He had a look at a lot of different places, and we wrote to Rami Mari, who was the author of that paper, and he had a look and agreed with us, and we were put in as the we were acknowledged as contributors to that error being found. Now
That's really cool.
So from there, basically the other thing that I found out about that particular change is, even though the initial images that I saw were from before perihelion and after perihelion, even after perihelion, some of the images still showed those ridges, and so I was trying to narrow down exactly when that collapse would have happened, and the collapse happened well after perihelion. So we're talking about when 67P was well out past Mars in its orbit, so not much should have been happening there. The ridge collapse didn't seem to be associated with any particular activity. It seemed with one image taken in January 2015 or 2016, it was there, and that was in January, and by the 1st of March, there was an image showing where it had already collapsed. So I could, by looking at more and more pictures, I could narrow it down further and further exactly when it happened, and trying to figure out what caused it.
So has, since so there's a couple of things I just want to go into first, and one thing is just like, for the person who is interested in the missions that are going on, specifically say Rosetta and the other missions that are going on, what are the kinds of resources that you go to be able to scan all these images? What is your typical sort of as you're kind of going through your journey through this, how do you do it?
Yeah. So basically, the only advantage a citizen scientist has over the professionals who are doing it there is perhaps knowing some inside information as to actually what's happening inside the comet that's causing these differences. Now, the mission scientists were relying very heavily on models. Now, the models take a lot of images and make a 3D model out of these areas. Now, the 3D model of this particular area, even at the highest resolution they would have had one before perihelion and after perihelion, they show a very fuzzy ridge along there. Now, what's happening there is when the model gets created with automated equipment, when they find a difference between one photo and another photo of the 3D position of a particular part of the ridge, if there's an error, they'll assume that there's erosion, so they'll put it. It'll end up being fuzzy up and down. Well, if there's something different happening at that point, especially along the neck, where most of the action is happening beneath the surface of the comet, then you will only really figure out what's going on by looking at 1,000 photos and comparing them and doing the 3D
Right.
imagery in your own brain.
So sorry. So I just wanted to know, like, where you see your 1,000 photos. Like, where did you?
So they published the Rosetta published all the photos after a 6-month period
Right.
of. So they published them all on a image viewer browser, and the link was there on the blog, and so there's essentially navcam photos were released well in advance, and the navcam photos are sufficient to see most of these changes that Andy and myself were looking at, and it was
So they
really,
were, because like I remember we were all pretty frustrated that the higher
yes,
resolution images weren't available, and we had to wait for the, we had the
yeah,
lower resolution. And occasionally they would throw us a bone, but
yes,
mostly the scientists were holding off. They were hanging on to the higher resolution images till they could do their
yeah,
science work, and which is different from how say NASA does it. So, but you were able to, you found that in even the lower, in the navcam stuff, you were able to see the kind of resolution that you're hoping
yeah.
for.
Yeah, so the biggest advantage that I had really was because the models were being made using the high res pictures, but the scientists were only comparing one model from before perihelion and the other model after perihelion, because they weren't trusting their own sense of what the 3D shapes were doing just by looking at photos themselves. So, in a sense. Uh, Even though they had an extra 6 months, or with the a serious high resolution of almost 2 years start on looking at these things, if you realize that the models were going to be fuzzy because there's lateral movement in those areas, then you'll get a much better idea of these sorts of things if you look at the photos and just use your own ability to figure out 3D shapes and how they morph.
Now, is there still, have you had a chance to spend any time with the images from, say, Hayabusa and the material that's coming out so far from the OSIRIS-REx mission?
Yes, I've been extremely interested in both those missions because there's a few things that are happening there. They're bringing a sample back, and I've got a feeling that there's going to be very interesting results there, but they're a few years away yet. Especially the Hayabusa mission, they're sending an impactor into Ryugu, which may well show some outgassing. Now, I did some research on papers that are showing active asteroids, and there were several asteroids that were active, and that included Ryugu. They had found some activity at some point in time in that peer-reviewed paper that I looked at. So the impactor, which I think is a shaped charge impactor, so it's like a shell from a cannon essentially, and the copper plate turns into a teardrop shape and should be able to penetrate into the asteroid and go to underground layers, which should have volatiles of some sort, and should outgas with some sort of continuous explosion for a fair while. So there should be some gas and dust coming out of Ryugu from the impactor for sure. Now that might be the better way to get a sample, because a lot of that should fall back onto the asteroid at that time. So that at the moment is the most interesting thing that's coming up that I've got some ideas about.
Right. Now, obviously, as a person who isn't in you're an outsider to the scientific
Yes.
community. You aren't working with the ESA team. How,
Yes.
And I know that you have your own theories about what
Yes.
is causing the bilobed shape.
Yes.
How has that been received compared to sort of what the scientists are proposing?
Well, the idea that both Andy and I have been proposing has been roundly ignored, I guess. There was there was two blog posts done with a guest author, I think it was Massaroni, who wrote into the Rosetta blog responding to some of the queries we had regarding the paper that he brought out that showed that they were formed by a collision. There were several issues with the simulation of that collision that was done from models, and the main issue was that the simulation they showed, which was a real model of two objects colliding and causing a shape like 67P, they used bodies that were about a quarter of the mass of 67P lobes, and they were going at an extremely low speed. So we described it as baby crawling speed. The scientists were talking about bicycle speeds being a possible speed that the lobes could have impacted. Now, when Andy and I calculated what that would actually mean for lobes that were far bigger, that is Rosetta lobe-sized lobes, the impact, because they're far more massive, the impact was about 16 times as much in terms of energy, and so that the models could not possibly have shown two lobes of that size to stick together and still be intact as separate lobes. There would have to be a way to slow them down. And the other thing we were looking at was the possibility of two accreted close to spheres being in the proximity of each other to be in a position to collide in the first place. There's a lot of statistical issues with that, and they've gotten around that by saying that we don't really know what was happening 4.5 billion years ago, and if we can see the two lobes are together now, so there must have been a way that they would have got close enough and slow enough to collide. So there's not too much we can argue with that. We can say that it's impossible, but I can't prove that it's impossible.
But it sounds like, I mean, just being able to carefully watch having more eyes on the comets and the asteroids that we're getting these pictures back from, and being able to spot out, I mean, being able to see a cliff collapse on a comet like that and be able to let the researchers know, I'm sure that kind of, that at the very least is pretty interesting for them to add. Well, we got to move on to the rest of our work. Marco, where can people find out more about what you're doing?
Well, I'd love you to follow me on Twitter. My Twitter handle's Marco Parigi 1, and that's the best place.
Okay, great.
I do have a blog and a few other things, but they're not as active as my Twitter. So certainly I'll be I'd love to have more followers there to discuss different theories that are going around, because there's a lot of them.
Yeah, cool. All right, well, thanks so much for joining us on the Weekly Space Hangout. And you're going to stick around as we go through the news. Okay, great.
Okay.
All right.
If there's any questions, I'll listen out for them, and yes, if appropriate, I can answer them.
Yeah, sounds good. All right, let's move on. Before we get on with the rest of the story, so I just want to sort of show people these sad pictures of the SpaceX Starship. So this is, of course, what the Starship, I'll show my co-host here. This is what the Starship was supposed to look like. Here, the Star Hopper, this is the prototype. And last night, hurricane force winds came through and knocked the nose cone over. And it just sort of collapsed like a pile of aluminum foil.
So that's what the real thing's going to look like, right?
Well,
The prototype. That's what it has to look like now.
This is exactly. This is the prototype. They're going to fly this thing. Over the last week or so, Elon Musk did a bunch of interviews. A pretty interesting one that happened with Popular Mechanics. Talked about some of the design choices that are going into the Starship. And this is just the prototype, of course. The first thing is they're going to be using 301 stainless steel. And one of the benefits of this is that it leaks, that it bleeds water. And so apparently they're going to be pumping water close to the skin of the rocket, and it's going to be coming out these tiny little perforations, these holes in the skin, and helping to cool the thing down.
Will that make it more or less likely to fall over?
It's exactly as likely to fall over. But it is obviously a bit of a setback. But if you look at, before it had fallen over, Musk had said, oh, it's going to launch in about 4 weeks. But he said maybe 8 weeks if something unforeseen happens. This, I think, would count for something unforeseen. So my guess
Gonna
is...
have to get in there with a lot of hammers and ding out those.
Yeah, exactly.
Yeah.
Anyway, we'll, of course, keep you posted in all things Musk. Morgan, what do you got?
I've always been a little skeptical of the idea that there's a Planet 9 just hanging out there that we haven't discovered. And so I was quite happy to see, or quite interested, I should say, to see a bit of modeling work done and released this last week that suggests that there are, in fact, other ways that you could get why we need Planet 9. So the whole idea behind why Planet 9 or something like it should be there is we've been seeing more and more of these Kuiper Belt objects. And these objects all have orbits that are aligned in kind of an unusual way. And it would be very unlikely for something like that to happen by sheer luck. So something out there with gravity has to be tugging on all of these Kuiper Belt objects and aligning their orbits over the course of millions or billions of years. And one possible way to do that is to have a planet out there that is torquing all of those orbits and sort of shifting them to line up with one another. But the nifty thing about gravity is that once you get away from something, it's hard to tell if you have like what physicists would call a point source, which is all the mass in one place, or if you have a distribution of mass that when you're far enough away from it looks like it's all in one place. And so it could look like a planet gravitationally without being a planet like in a physical sense. And that's basically what this study shows, which is they looked at other nearby star systems and observed that many of those that we can see the structure of have these far out belts of material. And probably they're made of ice given the temperature region we're talking about in the solar system. And so they basically started modeling these far out disks and looking to see, do they create the alignment of Kuiper Belt objects that we observe? And of course, most of the time they don't. But if you have a disk with the right amount of mass and tilted itself in the right way, it will generate a gravitational influence on these Kuiper Belt objects that reproduces basically what we see. And that's by no means proof that this is what's happening, but it is basically as good as the proof we have for Planet 9, which is the same basic argument. If you put a bunch of mass out there and let it interact gravitationally, you get what we see. So now we have two totally different ideas about what's happening, neither of which is particularly observable, and neither of which is probably that easy to disprove either. But it expands the realm of possibilities, and that's always a useful thing.
But doesn't it, like, the Planet 9 side of it is provable with larger surveys. You could get to a point where if there is a planet, if there is an object out there that is the size that they are expecting, it will be they don't find it beyond a certain size, then they'll know that it's
true.
not there.
Right now it would be a challenge to observe Planet 9, but in the not so distant future, it will be possible in principle to find something of this size. It'll just be a very painstaking search that astronomers will have to spend a lot of time on. But it's good to know that if we don't find it, that there are other hypotheses, and every sort of missed sighting of Planet 9 where we think it should be will probably crank up the likelihood of these other possibilities by sort of an equivalent amount.
Yeah, I have to say I was also very excited to see this particular theory, not because I dislike the idea of a Planet 9 or that I was very skeptical about it, but because I think a lot of us lost sight for a while that the Planet 9 theory was in fact just a theory, an idea of what could be causing these orbits, and it certainly shouldn't have been considered as the only one. And like you said, it's not an unknown thing in physics for multiple different types of things to exhibit the same type of gravitational force when seen from afar. And we should remember that and make sure that we talk about all the viable theories until we actually,
Right.
have more proof of one.
The choice isn't Planet 9 versus no Planet 9. The choice is Planet 9 versus other competing hypotheses.
Yeah.
And although we haven't seen, we haven't seen it in like Planet 9 so far, we have seen these gigantic Kuiper belts around other planetary systems out there.
And that kind of sets up this sort of weird situation, because while we could find Planet 9 in, say, the next 20 years, it's very, very unlikely that we would observe directly this disk of small AC objects that's out there. So even though this disk very likely could exist because we see it elsewhere in the solar system, and if it does exist, could quite possibly justify the observations we've had so far, we might be in kind of the same situation we are with the Oort cloud, where we can be pretty darn sure that it's there, but never see it. Like 100 years from now, never see it. And that's always kind of an awkward place to be in. But if every other star system, or 80% of star systems we look at, has this kind of structure, then it's reasonable to think that ours does as well. And maybe a little less reasonable to come up with another thing in the solar system to explain observations that we're making, even if we can't see that thing.
Very cool. Kimberly.
Yes. So I don't know if you guys know this, but early on Monday, there was a lunar eclipse. It was pretty flippin' awesome.
Who saw it with their own eyeballs?
I was asleep.
I was asleep.
I was asleep because it happened in the early hours of the morning.
And you knew
Monday.
that you were going to have terrible weather, and so you didn't bother?
Yeah. The weather out here on the east coast of the U.S. was not the best this weekend. However, the eclipse was widely visible for most of North America, South America, Europe, Africa, parts of Asia. Millions of people saw this lunar eclipse, this brilliant bright red moon. And for those that were looking very closely, at about 4:40 in the morning Universal Time, there was a tiny little flash of light along the moon's western hemisphere near the equator. And essentially what happened is someone noticed, put a post on Reddit saying, "Hey, what's this thing?" It jumped over to Twitter, and people were like, "Oh yeah, that's a real thing. We see it in the video feeds from Morocco, from Spain, from the Netherlands, from the US. It was seen on multiple cameras at the same time in the exact same location." And the most likely explanation for this is that there was a teeny tiny meteor impact during the lunar eclipse just before totality, which is not a rare thing. The moon gets hit by stuff a lot. But it is incredibly rare that we would see such a tiny impact, and that so many people would be viewing it all at the same time. I think I saw somewhere on Twitter that this...
You see this with your naked eye, or like in a camera? Only if a camera was zoomed in.
I think only if you were looking at it through a camera lens or a telescope lens, or viewing it like a live feed on your computer through one of these enhanced lenses. It was a very tiny flash of light. And what they've narrowed it down to is something that was about 20 pounds and about a foot in diameter. Like, this is like the teeny tiniest little impact. Something that we would never be able to see with our naked eye on the moon if it wasn't an eclipse.
It's like a loaf of bread-sized rock.
Yeah, it's pretty tiny. So we'd never be able to see it if it wasn't a lunar eclipse and we weren't looking pretty closely.
But this, 10 years ago, people would have thought that was crazy. That this was this whole idea of these transient lunar, I forget the term. Anyway, there were people saw flashes on the moon, and they thought that things were crashing into the moon, and so then people started to set up these. Someone's going to put it in the chat, I'm sure. Someone put. So people started to put telescopes to the moon and cameras just watching the moon nonstop, and now they see them all the time, which is great.
Yeah, it's one of those things.
Crazy.
Yeah, I mean, it's one of those things like now we know that, these small impacts on the moon are pretty regular, and on other planets are pretty regular. What's remarkable is that it was caught so quickly because so many people were looking that millions of people around the world saw it. They started sending in all of their images and data and videos and doing a coordinated effort on social media, all these citizen scientists pooling all their resources together to see it, to measure it, to verify that it happened. It wasn't a camera malfunction or anything like that, to pinpoint where on the surface it happened to like within 4 kilometers. They figured it out in its size and possible mass in all of 24 hours using the power of social media.
Now, if this had crashed into the Earth's atmosphere, Arjun is saying, would it get through the atmosphere? I don't think so.
I don't think so, no.
No.
It'd be a big,
I'm not an expert in that,
shooting
but
star. It'd be a big shooting star.
Like a fireball, like a bolide, yeah. So then, but that also just tells you, like, if you want to go live on the moon, don't forget...
no atmosphere.
By the way,
the sky is falling.
Yeah. Now, one of the things that we still want to do is to pinpoint its location a bit more accurately than just like plus or minus 4-5 kilometers in any direction. And that's because the Lunar Reconnaissance Orbiter wants to go do a flyby and see if there was an impact crater. And LRO needs a bit more precise coordinates than that to try and pinpoint which of the many, many, many craters on the moon might have been caused by this tiny meteor. So if you have images, send them to social media. There's a somewhat coordinated effort with LRO, given the fact that they can't, access much of their data right now. But they're going to try and look for it.
Right. All right. Well, so speaking of the sky falling, I got one more quick little story before we move on to Paul. I'm so mean. I'm sorry, Paul. But
it's fine.
It's a segue. I've got to do this. So on January 18th, a Japanese rocket launched, an Epsilon Rocket 4, and as part of its launch payload, it launched a CubeSat called ALE-1 that is going to be capable of delivering a man-made meteor shower. So,
why?
Well,
because we
the
can.
ultimate and rich person entertainment now. You can forget fireworks. You can launch your own meteor shower.
Yeah.
Sure.
So this is, this is the long-term idea, is that you would end up with a time when you could summon a meteor storm above your location, pay enough money, and you could have the sky fall just like that.
Is that literally the whole reason? Is for entertainment, or is there a scientific purpose for it?
I don't know. I just heard so many people just astronomers going into a blind rage that
they did the same with the disco ball thing.
Entertainment. Sky Canvas, the world's first artificial shooting star project. So, I'll show you their website.
Humanity's resources being put to good use.
Yeah.
Hey, if it's a good time,
what reusable rockets buys you.
So what?
I'm only being partially facetious.
Are you not entertained?
So what do you think about this compared to some of the more permanent ideas that have been considered?
First off, you'd never see the shooting stars if there's that much light on the ground.
Yeah.
So they're suckering you in already.
Yeah.
I like it better than having a giant space billboard.
Yeah, we talked about that. I think we talked about that last week.
No, thank you.
Yeah. And of course, the previous space disco ball that already went up and astronomers are a little furious with.
I think this is like an interesting part of space policy because it's something that basically was never anticipated by the big treaties signed in the middle of the 20th century. Like, they were all concerned about, bombs in space and soldiers in space and missiles in space. And
didn't consider confetti in space.
But they didn't consider what 2019 would bring.
They didn't really think of commercial activity, period, in space, because when it's $1 billion to send a little thing up into space, it didn't make any sense. And so we're going to need to hash out a new set of space laws, basically, to facilitate these really small launches that are, now people can be able to launch whatever the heck they want into space. And there's nothing practically that we can do to stop them. So how do we How do we work around that as a global community?
Build a giant net to gather up space junk.
Yes.
We should do that anyway.
And then blow it up again.
No, I have no idea.
All right, Paul, what do you got?
All right. Speaking of stuff blowing up and being awesome, we have Sagittarius A star, which is the giant black hole in the center of the Milky Way galaxy. And we're not taking pictures of the black hole itself yet. That's up to the Event Horizon Telescope. But there's all sorts of stuff around it that is all hot and glowing. We can take pictures of that. And we know that when black holes feed, when gas falls in, it forms accretion disks, it forms jets. And we're just now using networks of radio telescopes, being able to get some images of what that jet looks like. And it turns out, it seems like the jet is pointed right at us.
At
Like
me?
we're getting blasted. You, right there. You.
Oh gosh.
Not me over here. I'm good. But
Just me.
you.
Thanks.
Just you.
Thanks,
Very highly
Sagittarius A
concentrated.
star. I feel loved.
So actually, Paul, I sent you a link just before we got started, and it is the same thing.
Yeah.
Same story. Yeah. Okay. All right.
Same
So
story.
why
Pretty
is
picture.
this like? Why did this take so long to shock us? It seems like if we've known for a long time the mass of our supermassive black hole based
Yeah.
on its gravitational influences, and we've known the brightness, and we can look out at the galaxy in the universe and see a bunch of those everywhere. Why did this not seem anomalously bright given the amount of mass that the black hole has?
It seems, well, the brightness of the jet is connected to the mass of the black hole, but it's also connected to its recent feeding episodes. If you're a bigger black hole, then it's easier to feed, you're hungrier, and so you'll have more energetic events more often. But that doesn't stop smaller black holes from, having a gorging every once in a while. So maybe we caught Sagittarius A star like right after Thanksgiving.
So now that we sort of know that this radio jet is pointed right at us, are there new things that we can learn about this supermassive black hole that we couldn't if we didn't know where the jet was pointed?
Sure.
Cool.
But when when I imagine the supermassive black holes, I think of all the pictures we've ever seen. You've got the galaxy is like this disk, the supermassive black holes in the middle, and the jets are perpendicular.
Like, right.
To the. So now, are these the same jets, or is this like a different jet? Are
Right.
radio
So when
jets
you're
different
thinking
from...
of those big old radio jets, those are from active galactic nuclei. Those are massive powerhouses where the jets themselves extend like light years out, or tens of thousands of light years out. And the jet axis can be all sorts of wonky angles. There's no obligation for that central black hole to be at the same axis of rotation as the galaxy itself. So you'll see all sorts of wonky angles. What we're seeing here with Sagittarius A star, our own black hole isn't an active galactic nucleus. It's not a giant monster that is actively feeding. We didn't catch it after Thanksgiving. We caught it after a snack. And so depending on how that material fell in, when it did, how it got disrupted, the orientation of our black hole, whether it's had any merger events or accretion events that tilted it over time. So what we have is it's a strong jet for our black hole, but when it comes to active galactic nuclei, it's a very, very weak jet that appears to be aligned, pointing right at it.
Did we not know the spin axis of the black hole in the past? Or do we know that we just didn't know it had a jet?
I think it's both. Honestly, I think it's both. We're not exactly sure of the spin axis. And then we didn't know, we figured it had a jet because pretty much if you're massive and compact and there's stuff falling on you, you're going to have a jet. But we didn't know how big it was, how bright it was, where it's oriented. I'm reading here the abstract for the paper. The size of whatever is sourcing the jet is just 12 times bigger than the Schwarzschild radius of the black hole itself. Like, this is a very small thing.
Yeah, and so this picture, for those of us excited and can't wait for the first pictures from the Event Horizon Telescope, everybody stop nagging me. I have no control over this. Sometime in the spring 2019, they tell me. this is like the next best picture that we've had so far. This is like one of the most, and I'll put the picture up again for people to be able to see, but this is like probably the best picture we've had of the area around the supermassive black hole, right?
Yeah, this is really solid.
Yeah. And so when you look at like the simulation is on the top and the photo is on the bottom. Yeah, the real image is by the telescope array.
Yes.
So you can't see what I'm talking about. You have no idea. I appreciate you
Well,
playing
I know.
along.
No, I have the article up in front of me.
Yeah.
Come on, Fraser.
Yeah.
I know. I can. Come on.
So I mean, when you look at what the event horizon is going to look like, the size of it, and then you got the unscattered imagery, that's amazing how close we are. You know what? I'm going to call this done. We got our picture from the event horizon. We don't need to go any further. The people who are working on the event horizon telescope can just stop. I think.
No, don't listen. I want those pictures. Don't listen to Fraser. Give me my event horizon.
It's about as good as it's going to get. This is great.
No. Shh. Don't listen to him.
We were promised a blob, and I see a blob.
I want a better blob.
A better blob.
Smaller blob.
Yeah. But they use an array of 13 radio telescopes. That's the same thing as what the Event Horizon Telescope did, just less telescopes. All right.
Breaking my heart here.
All right, let's move on. Morgan.
I think we've talked before about the fact that Saturn's rings are disappearing. And this is happening because material is raining down from the inner edge of the ring and hitting the atmosphere of Saturn. And the effects on the atmosphere were actually observed all the way back in the Voyager era in 1981. But it wasn't until the last few orbits of Cassini that we got sort of direct measurements of this rain happening, and then paired those up with some spectral observations that had been made with Keck here in Hawaii. And they told us that the rings are really, really not going to last a long time. It could be 100 million years, maybe 200 million years, but they haven't been around very long. And those studies back from last year looked and sort of estimated that they thought the rings had only been around for maybe 100 million years based on the rate that they were disappearing. And then some work that has just come out recently is the mass measurements of the ring. And so as Cassini was making these final orbits between the ring and the planet, it was shooting radio waves back to Earth. And by measuring the Doppler shift on those radio waves, we could figure out the gravitational tug on the spacecraft. And then by basically subtracting off the gravitational tug of the planet, which we know really well after more than a decade orbiting it, what would be left is the gravitational tug of the rings. And this was like the last most important measurement that we didn't know about for the rings of Saturn. And people thought that it was probably around the mass of the icy moon Mimas, which is kind of a middling-sized moon of Saturn. And what these measurements show is that it's actually less than that. It's something like 0.42 times the mass of Mimas. And what this tells us is that the rings must be incredibly young, because we have a pretty good guess at sort of how rapidly things get dirty in space. For the same reason the moon had this impact on it, there's just stuff floating out there, dust and dirt and stuff. And if the rings have been around a really long time, they would have picked up a lot of this dust. And yet we see rings that are really pure. And the lighter the rings are, the less time they would have to absorb dust before it reached the purity level that we see. And so if you thought the rings were old, you wanted really big, massive rings. And that's not what we see. What we see is that the rings are lighter than scientists expected. And so the study basically says that the rings could be anywhere from 10 million to 100 million years old. So really, really recent. And that's really cool, but also
really
kind of really, really young. That's kind of a big problem because all of the ideas that we have about how the rings could form depend or work much, much better with really old rings. And we really don't have a good idea about how the rings could form to be so young. But it's now like unequivocally true that they are young. And so we have these sort of theory and observation are at a standoff.
It's such a weird thought that when you think about the vast age of the entire solar system, that we are here at a time when we could see these rings. Like,
and that's really bothersome.
It really is,
because we don't like to be special.
No,
we don't like to be lucky.
No,
and
we
so
get to see
idea,
eclipses, and we get to see Saturn's rings.
Yeah, so one idea that people have put forth to explain this is that maybe these aren't the only rings Saturn ever had. Maybe there's this process where rings turn into moons and then moons smash together and form rings again, and that Saturn has had multiple iterations of rings stretching back over billions of years. And we're not lucky to see rings because there have often been rings in the past. We just happen to be seeing this particular incarnation. And what's so neat about that is it means that the other outer planets might have had big ring systems in the past too, because moons exist around the other planets. They could smash together or get hit by impactors. And maybe a billion years ago, Jupiter had rings the size of Saturn. We don't know. We'll probably never know. There's really no way to know something like this for sure. But it's possible that Saturn is the special one right now. But over the course of billions of years, all the planets have had a turn as being the ringed planet. And that's pretty nifty.
I find it unsettling to think that in the vast history of the solar system, the luck that we happen to be here to see them in this exact position, and that they'll be gone in future generations. That sucks.
Love them while you got them.
Yeah. Like,
yeah.
Just every precious moment. Just savor the time you can spend with Saturn's rings.
That's all we have.
It's all we have.
It's time.
All right. Moving on. I think we've got another one from Kimberly.
She's muted.
What she had to say, I'm sure, was fascinating. But
it was fascinating.
Yeah.
You missed it.
And we missed it. And she's not doing it again.
Yeah, I'm never saying those words again. Anyway, just a quick little update. Europe's extremely large telescope is moving forward. They just completed almost the final round of grinding for its secondary mirror, which is a little over 4 meters in diameter. It's 3 tons. This mirror, it's the largest convex mirror ever created, and it is moving into the very final stages, where it just needs to be polished up all nice and pretty before it goes down to the telescope site. And it's a pretty exciting thing that this gigantic telescope is moving forward more or less on schedule, given all of the other all the kerfuffle with the other big telescopes that has happened recently. The ELT, which is the largest of the upcoming telescopes, is actually moving forward at a steady pace, and they just hit a pretty awesome milestone with this. So I'm still crossing my fingers for first light in 6 years.
Yeah.
Yay.
So sorry. So which one is this? This is
the secondary.
The secondary mirror. Okay.
Right. So the primary mirror is going to be a giant segmented mirror. I think it has 5 pieces, and this is the secondary mirror that will be mounted above that. And I believe this mirror plus all of its support system is going to weigh about 12 tons, and it's going to be hanging above this 39-meter segmented mirror. So. Yeah, the mirror itself, just the mirror, weighs about 3 tons.
It's surprising to me how long it takes them to grind and polish these mirrors. I know with the Giant Magellan telescope, like they take years.
They do, and the part of it is that one, it's giant. So this is the biggest convex mirror, single piece convex mirror that has ever been created, and they're going to polish it and grind it down to an accuracy of 15 nanometers.
Wow.
15, and this mirror is 4.25 meters in diameter.
Ever get the chance, it's worth going to one of these places where they grind these mirrors. In the US, the Mirror Lab at Arizona is under their football stadium, and it's just so cool. The stuff they have to go through to make them work is just amazing. They have to, like, bake the mirrors while they're grinding them to keep the shape just right and keep the temperature constant. And it's just so cool to see them make this stuff.
But it'll be so incredibly worth it when all of this comes together. I mean, it'll be the largest aperture telescope that we have. It'll be incredibly precise, be able to get down to incredibly fine angular resolutions. It'll be looking at everything from exoplanet atmospheres to the first stars and galaxies in the universe to measuring the rate of acceleration of the universe's expansion. It's going to do everything, and its mirrors have a big task ahead of them.
And it's going to be complete the same year that James Webb is.
Yeah, now you've pushed it. It's going to be in the 30s now.
Is that when it's happening?
Done, Fraser?
Wait, no. Well played, Kimberly.
I know you were generous with that, but you've still jinxed it.
Oh, well played. Oh, man.
Done.
All right, I think we did we wrap up everybody's news? Did anybody have one more thing?
I don't have one more thing.
No.
Nothing else happened this week.
Nothing else happened this week.
Nope.
I just want to make sure we've got everything that we got listed there. Okay, great. Well, then let's wrap things up and give people a chance to self-promote. And before we move on to my co-host, I want to go back to Marco for patiently sticking with us for the whole episode. Marco, thank you.
Yes, absolutely. Thank you very much. Yes, so at the moment I am actually working on a propellantless thrust device with several colleague engineers, and it's like the M drive except 1,000 times better. And there's a little bit of new physics involved, like like the M drive. But yes, it's we're pretty confident in it, so we're going to build a test device.
All right. Well, let us know when you have a prototype that can take us to space.
Yeah, fantastic. All right. So just to follow me on Twitter, I'm doing a lot of tweets about that as well. Yeah.
All right.
So
awesome.
Marco Parigi 1.
Thanks for joining us, Morgan. What are you working on?
Well, if you want a better and more thought out explanation of what this news about Saturn's rings means, keep an eye on the SciShare Space channel, because I had a great time writing about what we should do with this knowledge and what it means for how we should look at Saturn. So that should be coming up, I think, in maybe a couple weeks. So keep an eye on that.
Kimberly.
Well, right now I'm working on an article about a surprising discovery hidden inside of a moon rock, which you can read about soon on eos.org. I can't tell you that. You have to read it. Aww. Look at that. That's how promotion works. You can read about it on eos.org or follow me on Twitter at AstroKimCartier.
Paul.
Always having adventures, and soon I will be going on a book tour to promote my book, Your Place in the Universe, Understanding Our Big Messy Existence, which is for sale at bookstores nationwide.
And you're also you're going to kick off that whole book tour by showing up on my YouTube channel on Monday to talk about your book.
Yes, it's going to be tons of fun.
Yeah.
And also I'm on the latest season of Science Channel's How the Universe Works, which is airing every Tuesday night in January and February.
Excellent. All right, so my quick bit of self-promotion is I've got a new episode coming out on the Guide to Space tomorrow, all about how sort of new stories about the habitability of red dwarf planets and how they mostly suck. So it's going to be just a sad news. But I'll throw a couple of bones at you. So check that out. That's out to patrons already and launching tomorrow. So check it out. All right, let me bring the gallery back. Here's all of us. Big thank you to all of my co-hosts, special guest, as always, to our good friends at the Weekly Space Hangout crew and everyone watching us this week. Thank you so much, and we'll see you all next week.
Well, thank you very much for having me.
Bye.
Bye, everyone.